Okay, does that seem to work? Yeah, it looks like that works. Okay, let's do this. So we are going to play around with Scuttlebot, which is a decentralized secure gossip platform, as it says here. And I've been getting into this. It's pretty cool. It's pretty interesting. It's got a lot of very cool pieces under the hood. Some of the crypto stuff is pretty fun to play with. The protocol is pretty well documented here in the protocol guide, and so the concept really of this, and one of the benefits of this is, for example, if I have, say, a phone or a computer or a phone on the same network with other folks, that rather than information flowing through all these central servers going up and down, that this gossip protocol kind of allows us to hopefully pass messages around on the local network. So rather than, say, my status post or update via Twitter or whatever going up to a server or a central service, and then me pulling it, and then someone else pulling it down, if I was kind of friends with or had accepted someone else's keys, then whenever we were near each other or were on our a local network together, that data would kind of sync in the background for us, kind of negating the need for a central server, which is really interesting. There's a lot more to it than this. You can watch this video to really check it out and get an understanding of how it works. But and there's a ton of benefits, but the thing that I'm kind of most interested in and curious about is really this gossip protocol and this potential for applications and information to flow on local networks between people rather than kind of up and down and through a central server. So we're gonna build a Kotlin client for this. So there's a couple different projects out there. So like I said, there's a GitHub, the GitHub repo. There's a fair amount of different utilities and tools and pieces that make up the Scuttlebot protocol and different apps like Patchwork. And this Scuttlebot thing is a Node version of kind of like the simplest Scuttlebot client, if you will. And you can run this with Node, and basically it puts a Scuttlebot kind of client or peer on the network. The other thing that you can check out is Manyverse, and so this is kind of this app that Andre Saltz is building, and he just released it a couple weeks ago, I think. And so this is actually an Android app that is written entirely, for the most part, in Node.js, and runs currently on just Android, but I think he's planning on an iOS port. But the app is all written in Node and Cycle.js, which is another JavaScript framework that Andre works on. So it's pretty interesting. It's pretty cool, but I if this whole thing is going to flourish and grow, right, there's going to be need for more clients and more of these libraries and things that work with this protocol kind of on native platforms. I'm not really sure about the whole viability of running Node.js in as a full-blown Android app. It certainly works, and it's amazing to see that he's gotten it to work, and the code reuse that he gets out of Node and JavaScript is pretty amazing. But I would like to write a Kotlin version of this, so we're going to go ahead and do that. So where do we start? So like I said, definitely watch this video if you don't know or want to get an understanding of what we're doing. The best place in terms of understanding the protocol is this very well documented protocol guide. So first thing that we're going to do today is kind of talk a little bit about this, and we're going to build this Kotlin client and some tools so that we could maybe build an Android app purely in Kotlin, or also, maybe in the future we might even translate this to Kotlin native so that it could work in a lot of different places. That would be pretty cool. But we're just going to write today. I think we're going to get through kind of the first two sections, maybe keys and identities. We'll talk a little bit about that, and then we'll talk about discovery and how peers on a local network might discover each other, without, even if there wasn't a network connection, right? So say the Wi-Fi's down at your house or at your office or whatever, Scuttlebot will continue to work, and you can continue to share information and pass information between clients, even if there is no network, right? So, it says here, Scuttlebot's a flexible protocol capable of supporting many different types of applications. Like I was saying, Manyverse and Patchwork, and those kind of the first applications are kind of this distributed peer-to-peer social network. So basically everyone on the network is identified, or you are identified by a key. It's this ED2525519 key pair. And it can represent a lot of things like a person, a device, a server, or bot. Like it says, it's normal for people to have several identities. So in order to kind of participate in the network, you have to have this key pair that you generate. Very similar to if you've generated a pair for GitHub or whatever that means, right? That's kind of a way to identify a person or a device on the network, right? So that way, again, there's no coordination, there's no permission required to create one. Anyone can join. It's not governed by any central entity, which is great. And again, the most of these apps like Patchwork and Manyverse allow you to attach extra information to that key pair in such a way that you can give yourself a nickname and an avatar and a picture, so that way people can kind of people aren't seeing just these crazy base64 keys all over the place, right? So. And true to the design of all of these crypto things, right? You're represented, right, in public by your public key, right? So, and the way that they format this, typically you'll see it. You take the public key contents and you base64 encode it, right? And then on the end of it, right, is kind of this designator that says this is what this key is for. In the future, right, this might change what type of key. There might be multiple different types of keys that you could use in the future, and so that way, kind of when you read and when you parse this, you can properly handle it, right? So, again, right, the beginning @ signifies this represents a public key rather than something else. We'll get to the protocol and the formatting, way more in depth later on. But when you see an @ sign in front of something, and then you see that final padding, that dot, that ED25519, you know that, hey, this chunk of data is representative of like identifying someone, right? So, so basically, these keys typically live in .ssb secret, and a mobile app, they'll live on the phone. And you have to be careful because you need these keys. You can't get there's no usernames or passwords or anything like that. These keys are your identity, so they're pretty important. So discovery. So this is where it starts to get interesting, right? So after you have an identity, like I said, this kind of decentralized protocol is a gossip protocol, and so it doesn't require internet connectivity and the ability to go kind of out to the internet for peers to talk to each other, right? So one of the ways it does that is that say two phones are connected to a local network, or maybe they're nearby with Bluetooth. I think Andre was talking about there's a ticket open in the Manyverse repo that talks about adding kind of Bluetooth discovery connectivity locally, which would be pretty cool. So basically, these peers and this Scuttlebot utility, right, when you start it up, it actually starts broadcasting UDP packets on the local network, right? And they have this format that basically, if you listen on that peer or on that port on the network, you'll start to see people advertising that hey, I'm around, right? And so this is how people find each other when they are on the same network, right? But they don't necessarily know each other, right? So that's what we're going to kind of work on today is building kind of this a peer discovery thread, if you will, that can run in the background in any of our applications that can listen in and parse this material. And it says current implementations of these broadcasts 1 packet every second. When you see that peer, that allows you to connect and exchange messages, and then once you in terms of connecting, that's where things get really cool. There's this crypto thing called Secret Handshake that defines basically how these two peers can mutually authenticate, agree on a handshake, and ensure that when they communicate, right, that everything is secret, right? And so you can read this. This is really cool. Basically, the idea is you derive a set of shared keys. You can mutually authenticate on both ends, and then the shared secrets that you have are forward secure. So basically, you can't eavesdrop or replay or anything like that. So which is really wild. So we'll get into that. But first things first, we need to be able to see and identify peers on the network. So let's go ahead and start doing that. So I have just this basic sample project. I've called it Spot Kotlin, kind of keeping with the names, if you will. This is from a different project when I was messing with stuff, so we'll rename this. Can't rename root module. Okay. All right. Well, we'll fix that later. Okay. So the idea is we need to start a socket, or we need something. We need like so we're gonna create a new Kotlin file called discovery, right? And so this will be where we can discover peers locally, right? So let's create a class land discovery thread. So we're gonna need a socket, right? And it's gonna be a UDP socket, which is a datagram socket. Now we can actually give a default here, because it says UDP source and destination ports are set to the same port number that the peer is listening on. TCP for peer, normally 8,000. So basically what this is saying is that normally most clients broadcast and receive on their machine, device, whatever it is, on port 8008. So we can actually set this to be defaulted to 8008. What else? I think that's it. And this is going to be, we're going to run this in a separate thread. Maybe we'll make this an IO thing, a non-blocking IO thing later, but for now this can just be a thread for now. We're going to need a Boolean that says it's running, and this is going to be false to start, right? And then we're going to want to override the run method to do our work, right? So first thing we're going to do, we're going to set running equal to true, and then at the end we'll set running equal to false when it falls through, and then in here is where we'll check things out. Okay, so what are we gonna do, right? So we want to do while running. Actually, yeah, we're gonna do it this way, while running, and then in here, right, we're gonna. The idea basically is gonna be like read on the socket you know, parse each line, or well, we're going to attempt to parse each line as a peer, and then at some point, right, we'll probably need to take in like a handler of some sort here, so we can say like notify handler of peer, right? So that way, you know, whoever's using this thing can actually connect. So okay, so read on the socket, right? So we need a we're gonna have a datagram packet. Oh boy, so we need a buffer. And the question is, how big should that buffer be? So there is actually and something we should probably look at is SSB ref. So there's this reference kind of utility library in here. Yeah, for checking if things are valid references. So it lets you check things like links and feed and message IDs. And I feel like I remember seeing in here, yeah, so we can't always assume that the thing is just this simple IPv4 address, right? It could really be any network address, but for now, that's a typo. For now, let's just work with IPv4. I'm on an IPv4 network, so that, you know, that should be fine. So let's just assume that for now, and what that means is, well, let's just make this thing arbitrary large, right? So we're gonna have what are we gonna need? We're gonna need a buffer that is a byte array, and we'll be, you know, for now we'll be silly and we'll just say that, you know, there's 128 bytes in that buffer. We'll reuse it, so we won't be anything using more of this. Again, we might need more of this just in case, because we don't really know how long this could ever be in the case of maybe we get you know, I don't know if, you know, you might be able to have like multiple addresses in here. I'm not really sure. So but you know, for now, again, we're just going to assume IPv4. So datagram packet. So this takes the buffer and the size, right? What does this take? Buffer for holding the incoming datagram, and then the number of bytes to read. Yeah, so that can be, actually, wait a minute. Why does it need that? Yeah, all right. We're just gonna do this. This is fine for now. We'll clean this up later. And so then we're gonna receive that packet, right? And so then we basically want to get the, okay, so we're, you know, we're reading, you know, potentially 128 bytes. We may not get that many on a given line or a given packet. So then we kind of got to scope this down, right? So the bytes that we're getting are basically the packet data. We're going to basically slice this down into a different array, and we're going to go from 0 until packet.data.length, right? Because that'll tell us, or size? Yeah, size. No, it's packet.length, right? Yeah. So now we have just this thing. We're going to say, you know, the actual message that we got, right? You know, let's look at that and inspect it just so we know what's going on. I have no idea why that's in the Nile package, but it is in Java. And then we're going to print, we'll just print that message, right, just to see what it looks like. And then after we've used it, we can then do we can we just like empty the byte buffer? I assume there's like an empty method. I don't remember what it is. Where is this? It's like clear, empty. Yeah. Okay. All right. Clear. No. Okay. I don't know what that is. All right. Well, we'll leave ourselves a message to empty or clear the buffer, and then also here we're gonna say socket.close. This might handle errors. Okay, so let's see how this works. Let's see if that even compiles first, right? So let's just write a quick main here. We're gonna do discovery thread equals discovery thread, land discovery thread. We're gonna start it, and we're gonna join it so that that doesn't go. Let's see what happens here. Okay, so so we're gonna start this thing up, and then what I'm gonna do is I'm gonna launch the Manyverse app on my phone, because this is like a peer that I have set up. And what we should see, oh, actually, you know, it'd probably be helpful to see that this thing has started up. So started land discovery. That might be helpful. So we're going to start it up, and we should see nothing. And then what we'll do is, we don't need this. Maybe that's why my computer's freaking out. So we should see nothing, right? And basically it's blocking here, because this is a blocking thread. So it's waiting to see a packet, right? And then it'll fall through and parse. So I'm going to start the Manyverse app. So this is now running, coming up. And hey, we see some packets, which is pretty great. It's kind of odd that we're seeing it double like that. But that may be because we're not clearing the buffer. So yeah, let's make sure that we're doing that. God, what? How do we do this? I don't care about freeing the memory. I just care about a new byte array. Okay, well let's just make this a internal. Yeah, there we go. New buffer. Okay, so let's rerun this, and we shouldn't see double print every time, I don't think. We still are seeing double prints every time. Interesting. Let's rerun this and see. Parsing peer twice. Oh, you know what? It's because I'm on wired and Wi-Fi. Yeah, so if I turn this off, I'll betcha. Oh, I see nothing. Oh, there we go. Yeah. So now I'm only seeing one every second, or every however often this Miniverse app. Yeah. So now we're seeing one. Yeah. Okay. All right. That is great. Okay. Cool. So yeah. So again, right. This is the message that we see. Just like the protocol says, right? So if we stop, we're seeing net, we're seeing, another peer on this network, 8008, and then we're seeing like the actual identity, right? So this is we're seeing this thing, right? Which is awesome. Okay, so now, now that we have this, we can go ahead and parse this peer, right? So, we can make this we can make this an extension function, I guess, for now. So we're going to call it parse IPv4 peer. It's gonna return a discovered peer. And what does that thing have, right? So we have let's call it source type. So that's the net thing on the front. I'm not sure, it's not really clear what that means. I don't know if net just means the current network. I don't know if that changes, but we'll capture it, right? So we have a host. We're gonna have, which again, right, this is IPv4, but later that might need to be like a byte array or something else. We're gonna have a port. We are gonna have what else are we gonna have? The public key, right? That peer has. Okay, so we want to parse this thing out. So, yeah. All right. So, so first we're gonna, so we can kind of split it by colons, but not really, because there's gonna be this one weird thing in here that doesn't have a colon. So maybe let's do this like the really stupid, naive way first, where we just kind of go from the front, right, and see what we get, right? So our source type is going to be this dot subsequence of 0 until this dot index of this, right? And let's do this, right? So let's take this string and we will say this dot parse IPv peer, so we can kind of run this over and over again and see how we're doing here. Alrighty, so net. Okay, so that's great. So that's good. So then the host is subsequence of this dot index of the first until what's the yeah, I don't, maybe this isn't the right way to do this. Oh yeah, wait a minute. returns the index within the char sequence the first occurred. An index start index. Oh, we can send in a start index past where we are, right? So, and so we're basically going to the next thing, but our so our start. How am I gonna do this? Can't we do this? Name parameters? Why can't I name my parameters? Okay. Yeah, so the start index is going to be source type dot length plus 1, and then the range start index. Oh, that's the yeah. I don't like this. I don't like this way of doing this. We're just gonna split. All right, so the address and key parts is this dot split into this, right? So so basically, if we don't get 1, 2, 3, 4 things out of this, or no, let's do something different. Let's let's do this. Okay, so then basically let's look at this, right? So we're gonna get 4 pieces out of this, or 1, 2, 3, 4. Right? Yeah. Okay. So then we can say, so then we just have to clean up this port and the secret handshake gobbledygook. I don't know why that is. I don't know, but that's a little strange. I don't know why you wouldn't put a colon in there, but who knows? People are a lot smarter than me. So okay, so we're then going to say the port is 0, 1, 2. So address key and parts is 2 dot split on this, and that's going to be the 0 item. Right? Yeah. Okay. And then everything else, I think we're good on. So basically, this is gonna return a discovered peer. And we have everything we need. We can say discovered peer, address and key. Well, we can name these parameters so we know what's going on. Source type is going to be address and key parts of 0. The host is going to be address and key parts of 1. The port is going to be the port.toInt, and the public key is going to be address and key parts of 0, 1, 2, 3. Right? And this could use a lot of work. Very unsafe parsing. Do better. But that means we should be able to say discovered peer equals message dot parse IPv4 peer, and then if all of our stuff is correct, we can print that out. So let's see what we got. We got nothing. What? Oh, yeah. Yep. That would be why. Okay. All right, so we started lane discovery. Let's make sure this manyverse thing is up. Yeah, discovered. So yeah, so net. There's that, and that's all the information. So that's working. That's cool. All right. Well, that was a lot easier than I thought. Let's for now, let's add a no, this is not a, this is an interface. So let's take in a handler that is a discovered peer handler, and then we can handler dot handle is weird. Let's call it notify of the discovered peer. Yeah. And then we don't need to do this anymore. Actually, you know what? This should be what's the best? I always forget what this stuff is in Kotlin. We want a new discovered peer handler. What is this? I don't remember this syntax. Kotlin SAM interface. Dun, dun, dun. What do I want? Oh, yeah. So this should just be peer, or at least I think this is what we can do. How do I define this in Kotlin again? I don't remember. Oh, right. Yeah. We don't want to do it this way. Yeah. That's the Java way. Yeah, the handler needs to be discovered peer, and then this. Is that right? Why does that look so weird? Man, I really don't remember how to do this. I haven't done this in forever. I haven't done this in a long time. Yeah, SAM constructors. Kotlin's able to do this. Let's actually, yeah, so people that use this may use this from more than just Kotlin. So if this is like this, then our handler needs to be a discovery peer handler. And then I can just do this. Kotlin is. I just don't remember this. Functions and lambdas. Functions. Do-do-do. Man, Kotlin pass lambda as argument. This shouldn't be that difficult. What is the syntax for this? What is the syntax for this? Uh-oh. So we're gonna pass in the discovered peer, and then this is gonna be unit, right? Yes, yes. Yes, that is better. Much better. Yeah, this is the Kotlin way. Okay. Yeah, we'll get rid of this. If we want to make this more interoperable with Java later, maybe we can. But for now, this is fine. Okay, so let's start up Miniverse. And yeah, we're seeing appear. Cool. So this is running Miniverse, and we're seeing that appear. And if we kill the app, then it stops. So that's pretty good. That is good enough for today. One thing we can do, actually, we can change these to let's see. So we have in our Gradle, we have proper logging things. So let's create that and not use print statements. What is it? Get logger, right? Hope I got the syntax right. Get logger. Yeah, land discovery thread. And then this will be, you know, we can just say here, right, like logger dot debug sheathed message. We received the packet, right? And then logger.debug. And this can be, yeah, at some point this might be no good, right? So like even in the very basic case where you can say like if address and key parts dot size does not equal 4, right, we can return null. Oops, null. Right, that's just, you know, simple, right? So then basically, right, we can say, you know, discovered peer dot let logger dot debug $it, and then we can only notify the handler if we got a peer. We can do this and only use this from main. so let's just rerun that real quick to make sure everything's okay. Oh, we gotta fix this too. Logger.debug. Fix this. All right, so let's start this back up. Start Manyverse back up. We started it. It's starting. We're receiving a packet. Discovered a peer. All right, cool. So that seems to work. That's about all I was planning on getting to today. So we will call that a great success. I'll put this code up on GitHub here in a minute. And yeah, so actually let's real quick, let's do a readme so we can kind of keep track of what we're doing, right? So we are making a Kotlin ports of Scuttlebot. Our to-do list is probably going to grow quite long, but basically today, what is the GitHub list, to-do list, markdown, syntax, task lists, yeah, it's this weird thing, right? So it's dash, okay, so today, we create a discovery thread to listen for peer broadcasts, right? So okay, so that's what we did today, which is good. So next thing, we definitely need to improve parsing of discovery packets. What else? We're going to need to implement the secret handshake once we actually parse that, right? That's where we really get into the meat of the protocol and the crypto stuff, because we need to start this whole handshake process where we exchange keys and that sort of thing, right? So that's really kind of like probably the big next thing we're going to do, and maybe we'll break this down, right? We'll implement initial what is this called? The implement initial key exchange, right? And then we will, what's next, right? Implement key exchange client hello. Server's going to do something, and then basically like implement shared key derivation. That'll be next. That's probably plenty for now. So yeah, so I'll put this up on GitHub in a little bit, and we'll pick up where we left off next time.